Welcome to this video. Today, let's explore a fascinating geometric illusion, Hooper's paradox. We start with a geometric shape. Its area, exactly 32 square units. Now, we cut this shape into 4 parts. Then, we rearrange them into what looks like a neat rectangle. But hold on, when we calculate the area of this new rectangle, it's only 30 square units. So, where did the 2 missing units go? This is the mystery behind Hooper's paradox. It was first published in 1774 by William Hooper in his book Rational Recreations. But let's look closer. At first glance, the dissected parts seem unchanged. Especially the triangles, they look identical. But in reality, they're not. In the original shape, one triangle has a shorter side of 2 units. In the rectangle, that same side is only 1.8 units long. That tiny difference means the 2 triangles overlap when rearranged. And that overlap forms a shape, a parallelogram right in the center. Let's do some math. The first diagonal of the parallelogram is square root of 2 squared plus 1 squared equals square root of 5. The second diagonal is square root of 3 squared plus 10 squared equals square root of 109. The sides of the parallelogram are square root of 2 squared plus 6 squared equals square root of 40 and square root of 1 squared plus 4 squared equals square root of 17. Now we apply Heron's formula for triangle area. We plug in the values, calculate carefully, and the final area of the parallelogram comes out to exactly 2 square units. That's the area that went missing during the rearrangement. So, the shape didn't shrink, it just hid part of itself. A clever illusion, right? So what have we learned? This paradox isn't magic, it's math and illusion working together. A small shift in shape, and our eyes are completely fooled. Thanks for watching. If you like this mind-bending paradox, don't forget to like, subscribe, and share it with friends. See you soon. Have you ever heard that adding a road to a traffic network can actually make travel times worse for everyone? It sounds completely backward, but it's true. This is Hooper's paradox. Here's how it works. Imagine a city with 2 points, point A and point B, connected by 2 separate routes. Each route has 2 roads, one short and one slow, but traffic spreads out evenly, and drivers take the best paths based on current traffic. Now, suppose we add a new shortcut connecting the 2 middle points of the old routes. Logically, adding a faster path should help, right? But here's the paradox, everyone starts using the shortcut because it seems like the fastest route. The result, congestion increases, and everyone's travel time gets worse than before the shortcut existed. Why? Because each driver acts selfishly, choosing what seems best for them without considering the overall system. The new route tempts drivers into patterns that overload certain paths. This paradox was discovered by Dieter Brace in 1968. It's a classic example of how individual optimization doesn't always lead to system-wide optimization. You'll see versions of Brace's paradox in traffic systems, internet routing, and even electrical grids. The takeaway: sometimes, removing a road or limiting choice can actually improve overall performance. It's a powerful lesson in systems design, game theory, and why human intuition doesn't always match how complex networks behave. Let's dive into the Russell paradox, a famous problem that shook the foundations of set theory. In basic set theory, a set is just a collection of objects. Simple, right? Now, imagine this: some sets can contain themselves and some can't. For example, the set of all sets is supposed to contain itself. But what about the set of all sets that do not contain themselves? Let's call the set R. So, R is defined as the set of all sets that do not contain themselves. Here's the twist: does R contain itself? Let's check both possibilities. If R does contain itself, then by definition it should not contain itself, because it only contains sets that don't contain themselves. But if R does not contain itself, then it satisfies the condition for being in R, so it should contain itself. This contradiction, where R contains itself if and only if it does not contain itself, is the Russell paradox. Discovered by Bertrand Russell in 1901, this paradox exposed a fundamental problem in set theory, the idea that any definable collection is a valid set. To fix this, mathematicians developed more rigorous foundations, like Zimmerloh-Fraenkel set theory, which avoids such paradoxes by restricting how sets can be formed. The Russell paradox shows that even in math, self-reference and unrestricted definitions can lead to contradictions, and that careful logical structure is essential to keep things consistent. It's a reminder, the moment you allow a system to talk about itself freely, paradoxes start creeping in. Let's talk about the Berry paradox, a classic example of how language can trick logic. It goes like this. The smallest positive integer not definable in under 20 words. Sounds innocent, right? But now ask yourself, what number is that? Here's where it gets weird. That sentence itself has only 13 words. So if there really is such a number, we've just defined it in under 20 words. But that's a contradiction. If we can define it in under 20 words, then it's not the smallest number that can't be defined that way. So, what's going on? This is the Berry paradox, named after the librarian G.G. Berry. It's not a mathematical contradiction, but a semantic paradox. It arises from the self-referential use of language. The problem is that phrases like, not definable in under 20 words, depend on the language and the rules we allow, and we are using those rules within the same language to make the definition. This creates a kind of loop or circular reasoning. In more formal settings, like logic or computer science, we avoid paradoxes like this by using strict systems, like Gödel numbering or formal languages, to clearly separate object-level statements from meta-level statements. The Berry paradox teaches us an important lesson. Even simple statements can lead to deep contradictions if we are not careful with definitions and self-reference. It's not just wordplay, it's a glimpse into the foundations of logic, computation, and even the limits of mathematics itself. Have you heard of the Banach-Tarski paradox? It's a result in pure mathematics that sounds completely impossible at first. It says, you can take a solid sphere, like a ball, split it into 5 pieces, and then just by rotating and moving those pieces reassemble them into 2 balls, each exactly the same as the original. No stretching, no shrinking, just rotation and movement. Sounds like it breaks the conservation of volume, right? But here's the thing, this paradox doesn't apply to physical objects, it's purely mathematical. The trick lies in the use of the axiom of choice, a principle in set theory. It allows us to select elements from infinitely many sets, even if we can't define a specific rule for how to choose them. Using this axiom, Banach and Tarski proved that it's possible to partition a sphere into pieces so strange and fragmented we call them non-measurable sets, that they don't have a well-defined volume at all. Because these sets are so abstract, they can behave in ways that seem to defy logic, like duplicating a ball. But in real life, these sets can't be constructed physically. They depend on idealized, infinite precision. So you can't actually create 2 basketballs from one using this method. What the Banach-Tarski paradox really shows is how infinite mathematics and set theory can lead to results that completely break our everyday intuition. It doesn't violate math, it stretches what's mathematically possible when you accept certain assumptions like the axiom of choice. In short, it's not a magic trick. It's a reminder that the math world can be a lot weirder and more fascinating than the physical one. The paradox of the infinite chessboard, the power of infinity in ancient India. Imagine a chessboard. A normal chessboard has 64 squares, 8 rows and 8 columns. But what if the chessboard didn't stop there? What if it stretched infinitely in all directions? In ancient Indian mathematics, the concept of infinity wasn't just abstract. It was used to solve real-world problems, and it laid the groundwork for many modern mathematical ideas. Now, picture this. On this infinite chessboard, you place a single piece in the middle. Every time you move, you double the number of squares you cover. You start at 1 square, then go to 2, then 4, then 8, and so on. You keep doubling the squares. After a few moves, you'd cover a large area. But here's the paradox. No matter how many moves you make, you will never cover the entire chessboard. Why? Because the chessboard is infinite. In the Indian mathematical tradition, particularly in Vedic mathematics, the concept of infinity was understood in a way that's almost identical to how we view geometric series today. Indian scholars used this idea to explain infinite sequences, and it forms the foundation of calculus. Let me explain. The paradox comes from the idea of infinite sums, an infinite number of steps that never quite finish. Let's say the chessboard stretches infinitely, and you double your steps each time. Mathematically, this is like an infinite geometric series, where each term gets smaller, but the total number of terms never ends. But here's the twist. Even though you have an infinite number of steps, the total distance you travel could still be finite. This is an ancient paradox that comes from the Indian understanding of infinity. They were aware that by adding an infinite number of terms, the sum could still be finite. This understanding was far ahead of its time. In the case of the chessboard, if you double the number of squares each time, you get closer and closer to covering the entire chessboard. However, since the chessboard is infinite, no matter how many moves you make, you'll never completely cover it. But interestingly, infinite moves can still sum up to a finite total. This paradox is deeply linked to the Indian concept of ananta, which means infinity. Indian mathematicians in ancient texts like the Salabha Sutras used the idea of infinity to solve problems related to geometry and measurements. Their methods foreshadowed many modern concepts in calculus. The paradox shows us that infinity is not just a theoretical idea, but a practical concept embedded in our understanding of space, time, and numbers. Now, how does this paradox apply to real life? Think about fractal geometry, a field that studies patterns repeating at every scale. In fractals, you often see infinite detail, even though the space you're looking at is finite. The Mandelbrot set, for example, has an infinite number of points, but we can't reach the end of it, no matter how much we zoom in. In quantum physics, where the behavior of particles seems to reflect infinite possibilities, the idea of an infinite chessboard and infinite sums has real-world applications too. The paradox of the infinite chessboard asks, can you truly finish an infinite task? Can you ever fully cover something that goes on forever? The ancient Indian mathematicians posed such questions long before we had the modern tools to answer them. Their exploration of infinity was groundbreaking, and their ideas continue to influence mathematics today. So, let me ask you, do you think it's possible to complete an infinite task, or is infinity just something that keeps us from reaching the end? Let me know your thoughts in the comments. If you enjoyed this paradox, like, share, and subscribe for more discussions on mathematics. Because mathematics, like infinity, never ends. The ship of Theseus. Imagine a ship. It sails for years through storms and calm seas. But over time, the wooden parts begin to wear out. One plank is replaced, then another. Years pass, and every single part of the ship is eventually replaced. Now, not a single piece of the original remains. Here's the question. Is it still the same ship? This is the ship of Theseus. An ancient philosophical puzzle. It's not just about wood and nails. It's about identity, change, and what makes something truly itself. Now imagine this. What if someone collected all the old parts, the ones removed from the original ship, and rebuilt a new ship using only those? Which one is the real ship of Theseus now? The one with continuous history? Or the one with original materials? At first, this seems like a simple thought experiment. But it quickly becomes a deep question about life and identity. Because this isn't just about a ship. It's about us. From birth to adulthood, your body changes. Old cells die, and new ones replace them. In fact, most of the cells in your body today weren't there 10 years ago. You are literally not made of the same matter. But are you still the same person? What about your mind? Your memories shift. Your beliefs evolve. You learn, unlearn, grow, and forget. Are you still you? Now, let's look at technology. Imagine a computer. You upgrade the processor, then the storage, then the screen, the keyboard, and even the casing. Eventually, no original parts are left. Is it the same computer? Or take artificial intelligence. What if a machine could copy all your thoughts, your voice, your memories, down to the smallest detail? Would that machine be you? The ship of Theseus forces us to ask, what defines identity? Is it the physical material? Is it the continuity over time? Is it the structure, the function, or the story behind it? Some philosophers say continuity is key. If change happens gradually, the identity remains. Others believe identity lies in the original substance. If you replace all parts, it's no longer the same thing. And some are you. Identity is an illusion altogether. A story we tell ourselves to feel stable in a world that constantly changes. Let's take it further. Think about personal relationships. You are not the same person you were 5 years ago. But your friends and family still recognize you as you. Why? Maybe it's your behavior. Maybe your memories. Maybe it's something deeper, something invisible, like the soul or consciousness. The ship of Theseus shows up everywhere. In science, in religion, in ethics, in technology, and especially in the age of digital identity, AI, and virtual reality. The question is more relevant than ever. Who are you? Are you your body, your memories, your consciousness, or just the story that holds it all together? So let's return to the original question. If every part of you was slowly replaced, if your thoughts, your habits, your body, your beliefs, all changed over time, would you still be you? Or would something else take your place? That's the mystery of the ship of Theseus. And it's not meant to give you an answer. It's meant to spark a question. A question only you can try to answer. Let me know what you think in the comments. Would love to hear your perspective. If you enjoyed this thought experiment, hit like, share, and subscribe for more. We'll explore more puzzles of identity, existence, and the strange corners of philosophy. Because even ideas evolve, and so do we.